I think you start out with this idea of what it's going to be like, and then when you do finally look at the Earth for the first time, you're overwhelmed by how much more beautiful it really is when you see it for real. It's like this dynamic, alive place that you see glowing all the time.
Hi guys. I wanted to revisit the Analemma because I wasn't satisfied with how I explained that, and there's good reason why, because when I went back and I looked into it, I realized there's a lot of factors there that when I tell you about it, it will totally make sense. Okay, the Analemma, it performs this figure 8 path. This is a full year, okay? So they will tell you that the Earth is spinning and it's tilted at 23.5 degrees and it's on an elliptical orbit around the sun, which is nonsense. It just doesn't make sense. Okay, this is the real reason why we have the Analemma. There's a couple factors involved. One, you'll see that the sun, as it moves from December, January, February, March, April, May, goes to the summer solstice and back down again like that. It's varying in velocity. On the left, it's slower than your clock. It can get up to about 15, 16 minutes slower. And then on the right, it's faster than your clock. So, as you see here, it turns the corner like that. Kind of think of it like a Grand Prix race car, as it turning a serpentine corner in the Swiss mountains somewhere. It's slow. You're slowing down to turn the corner, and that's exactly why it's doing that. See, and also you'll notice too that this white band right here, that's the Milky Way band. Okay, that divides the celestial sphere into two different hemispheres that have two different polarizing currents, which actually steers the sun. I did a video about this. I showed how the Milky Way band performs the function of steering the sun. It's not a spiral galaxy, okay? It has a function. It's also mentioned in Scripture, Job 38:9. It's called a swaddling band. And so, as you see this, when the sun passes that band, it slows down. It's almost like there's more dense matter near the band. So it's slowing down like that, but it's also steering, it's governing it to change direction like that. Okay, the sun is moving, it's connected, the backside of the sun is connected from the top of the pyramid there with rays of light. I've seen this in a hypnagogic vision before. I've seen the backside of the sun. But when it gets lower like that in the south, that band loosens, and so we have a wider range of velocity in the south as opposed to in the north where it's more tight. And so that's why the asymmetry, the horizontal asymmetry, it's pretty much vertically symmetrical, but the horizontal asymmetry is the fact that it gets looser. The sun gets closer to you. The sun is 32.7 minutes in the south as opposed to 31.6 minutes in the north. I'm talking angular diameter here. So every minute or every 360 degrees is divided up into minutes. And so, I'm sorry, yeah, a full circle is 360 degrees, and then each degree is divided up into minutes. And so we're talking about a half a degree here, but there's still a difference. And so the sun is actually getting closer to the Earth in the south, and I'll show you that in the next animation to come here. So that's what's going on. We have a couple factors involved here. Okay, now I'm going to also show you, I plotted out the sun for each specific day, the right ascension for the sun for each day of the year, and I'm going to show you from a top-down view how that looks. So let's go to that slide next, after we watch this in high res. Okay, here is the top-down animation that I created. Like I said before, I told you that I plotted each day of the sun, the right ascension of the sun, and what we see here is we see two objects spinning clockwise. Now the reason why the sun is spinning clockwise is because I'm not showing the daily rotation. If it was a daily rotation, it would be going the other way a lot faster. What I'm showing the whole year referenced against the celestial sphere. Normally the celestial sphere would be spinning, but I froze that, so now we can see the clockwise, the false rotation of the sun is moving clockwise. Okay, we see two objects here. This green object is another false sun, which is moving in a linear progression. It means that it has no acceleration or deceleration to it. It's just going perfectly linear. And that's so you can see the varying velocity of the sun compared to that. Okay, so here is the winter solstice, and here is the point where it crosses the meridian in April, around April 15th. Here's the summer solstice. That's where it crosses the meridian again, around June 21st or so. And then the end of August, beginning of September, it crosses the meridian again. See, it's higher than our equinoxes. Our equinoxes are over here. So that's because, like I told you, because when it gets in the south, it has a wider range of velocity. It's more elastic. So, as you see here, in the winter, when it starts in December, it's going to start out slow. Okay? Now, even though it looks like it's moving faster than the green, you have to think opposite here. So then it moves fast again, slow again, and fast again, like that. The Milky Way band is going across the top. It's 60 degrees on a tilt. Okay, it's not 60 degrees from the ecliptic. It's actually 60 degrees from the celestial equator. They say it's from the ecliptic because they think that the sun, they think that the Earth is on a tilt, but it's not. So, as it goes across the top here, it's tilted up forward toward you. That's why we see it's not a perfect circle. So the animation isn't anyway. And then when it goes along the bottom, it's going behind or below the tilt like that. All right. So with this animation, we can see the varying velocity of the sun. And this is an accurate plotting from Stellarium. So let's watch that in high res. Okay, this is a very important animation for you to understand what's going on. Like I told you before, when the sun goes into the south, it will get closer to the Earth. Okay, and so we see here in the south here, this is at 23.5 south, as opposed to 23.5 north. There is a difference in length. We can draw a line here to the Earth. Okay. As opposed to drawing a line from here to the Earth. We'll see that this line is much longer, well not much, but it's still longer than this line. So when you're here in the north, the sun is further away from you, okay? When you're here in the south, the sun is closer to you, okay? So that's why we have this horizontal asymmetry to the analemma. I also have this on a time lapse, so we're seeing the star trails move across like that. Kind of a neat effect. Now let's watch that in high res. So I want to talk a little bit about Ed Leedskalnin and his coral castle, where he actually constructed a concave analemmic sundial. And I actually went there in November of 2008. It was pretty fascinating. So I'm pretty sure that Ed knew that the Earth was concave. He didn't outright say it, but you know, he had a lot of secrets. And so if you'll notice, this is a concave surface. And another interesting thing about this as well is that, let me scroll forward here a little bit. You'll notice that there's like this chair, right? This chair or this throne, the vacant seat of God. If this is like a small scale model of the concave Earth, where you have heaven in the center. Okay, if you think of the top of the pyramid inside of heaven, and you have the earth below. Okay, you can't create a sundial on a sundial like this on a convex Earth. It doesn't work because the Earth is concave. Okay, just thought I'd bring that up because it's very, very interesting. I want to recommend you watch, here I'll give you the link to my previous video where I talk about the Milky Way and the function of the Milky Way, how it steers the sun. Also, there's another video where I talk about the biplanetary nebula, where there's actually an axis, a symmetrical axis going across this Milky Way band. So it has symmetry here. So everything makes sense within the concave Earth. So thanks for watching, and hopefully now you understand, now that you can visualize why things happen in the sky the way they do with our sun. So, talk to you later.